Hey folks, Paul Abernathy here. Welcome to another episode here at Electrical Code Academy. So on today's episode, we're going to talk neutral conductors. We're going to talk neutral point. We also are going to talk about services and bringing a neutral to the service, or better determined, a grounded conductor to the service, and what's the minimum size when how to calculate that neutral or grounded conductor. And what's the difference between using the terminology grounded or neutral? So we're going to look at it all today and try to clear up all those questions here when it comes to the neutral conductor. All right, so let's kind of get into it first. And so important that we learn definitions, because since 2008 edition of the NEC, we've had a definition of neutral conductor as well as a neutral point. That's the point on the system where the neutral conductor is connected. Okay, so that kind of derives the neutral conductor. Okay, so here we are. These are definitions. This is also, I should say, out of the 2023 edition of the National Electrical Code, and this is out of our grounding and bonding series. All right, so if you want to learn more about grounding and bonding and really get into the weeds, then check out our grounding and bonding program. It really does take you through more than just the electrodes and things. Like, you're like, I already know that stuff. I know ground rods. No, this gets deep. It talks about what systems are required to be grounded, ones that are optionally grounded, or not required, but you can. And then there's systems that you just can't ground. And there's certain things that's covered in our grounding and bonding series. So it, again, is one of my favorite series, but you might like it as well. But we're working in that today. Okay. And also should remind you that the 2023 edition of the Fast Tracks Black, as you see below, is available if you're studying for a National Electrical Code exam, or if you're an inspector studying for an exam, or you just want to get better knowledge of the NEC as a whole, a kind of a 30,000 foot view of everything, then this is the program for you down here. This program right here is purely grounding and bonding, not for exam prep. It is simply to learn the National Electrical Code when it comes to grounding and bonding aspects. Okay. All right, so let's look here. Neutral conductor. What's a neutral conductor? It's the conductor connected to where? The neutral point of the system, of a system that is intended to carry current under normal conditions. So if you think about that, it's that white conductor or that gray conductor or that conductor with 3 white or gray stripes other than green. Okay. So that conductor is carrying current, and it's expected to carry current. In other words, when you install it and you hook everything up, you know that at any given point it could carry current. Now, the neutral conductor, typically when we work with systems in an NEC, the neutral conductor is basically sized to handle the maximum unbalanced load. And we'll talk about that in 220.61 when it comes to a calculation of the neutral conductor, especially for things like feeders and services. But it's really important to understand that the neutral conductor is designed to carry current at all times under a normal condition. Very different from like an equipment grounding conductor, which does in the service connect to the same bus as the neutral conductors. But as it leaves your service and goes out, it's important to realize that the equipment grounding conductor is to carry fault current. And it's not expected to carry current under normal condition, only under an abnormal condition. Whereas a neutral is going to potentially carry current at any given time. So it's an important distinction. And it's why it's so important for us to talk about improper case to neutrals downstream, where you connect the equipment ground to the neutral conductor improperly, because what you're doing is you're imposing current over onto the metal parts, which are connected to the equipment ground. Because the equipment ground is serving dual roles, right? It's not only giving you a reference to Earth, but it's also being used as a bonding component. So it's vital that we understand those importances of not violating improper case to neutrals downstream. And we cover that in our grounding and bonding series, but it's so important that you understand those concepts as an electrician, especially when I look at social media and I see it done wrong so many times, that we want to make sure that you understand that that's a serious safety concern. Okay, so don't confuse an equipment grounding conductor with a neutral just because they connect together at the same location back at the service. Don't get them confused. The neutral is going to carry current or expected to carry current at any given time under a normal conditions, whereas the equipment ground is not, only under abnormal conditions, like a ground fault, okay? All right, so here you go. Now, other thing that's unique about our program is that we have discussions, and I want to read the discussion because this is a great discussion, because there's so many people out there that take let's say you have a 14-2 non-metallic sheath cable, okay? You got a black and a white, and you have this in the center, wrapped in paper. You have a bare equipment ground. Now, we understand the black conductor is a hot conductor. We call that an ungrounded conductor because it's not connected to ground in any way. And then you have the white conductor, which in a two-wire system like that, we refer to that as a neutral. Now, since it comes from a grounded system, it is actually a grounded conductor. And not all grounded conductors are neutrals, okay? But all neutral conductors are grounded conductors because of how they're created. So what creates a neutral? And we're going to be looking at that here, and that's the kind of the main topic here of this episode, is what defines a neutral conductor. And then, of course, we'll go on into the second part, and that's when we'll look at how it's applied to the service and calculations that you have to do, and what's the minimum size that's required by 250.102C1, and how that's applied. And we'll look at things like 250.24D, and we'll see how you're sizing those grounded conductors and things like that. So it's a lot. So make sure you buckle up for it, because we're going to cover a lot in this series. All right, so let's look at this discussion. Important. It says, this also was a new definition, neutral conductor was a new definition in 2008, okay? And as is illustrated in figure 1-17, and we're going to look at that, which is going to show you kind of the neutral point, which was also added to the code in 2008, and how a neutral conductor is derived. And I think that if you see that, it'll start to hammer home the importance of all of those safety issues of, again, not connecting equipment grounds to neutrals downstream, and all those things will start to come together, and we all become better electricians over it. In 2008, a correlating committee task group was charged between the 2005 and the 2008 cycle to look at the use of the term neutral throughout the NEC. And so they looked at it and said, you know what, we need to come up with a definition. Well, when they came up with that definition, they said, look, we need something else. Rather than go through all of the explanation of a neutral conductor, we need to show on the system, whether it's a Y transformer or delta transformer, or a delta that creates a zigzag secondary transformer or secondary system, what connection creates a neutral. And then it's important to make sure people are aware of what does not create a neutral. Even though a conductor is connected to Earth, based on where it's connected on the transformer, it doesn't necessarily make it a neutral, but it is still a grounded conductor because it's intentionally grounded to the Earth through the system. So all those things are important. So they had a task group that got together and they created it, and that's what caused them to create the term neutral conductor in 2008. And then, of course, they created neutral point as well. And all of these serve to help us better understand it. Now, if you look at these systems right here, a 122 40-volt single-phase 3-wire system is going to derive a neutral. A 122 40-volt 3-phase 4-wire delta system, depending on where you connect it in the midpoint of a winding, is going to create, obviously because it's a 120, it's going to have a neutral point, and we're going to derive a neutral. Then you have a 208 Y120 3-phase 4-wire Y system with a midpoint connection on that Y winding that's going to create a neutral point. And then you have 480 Y277 volt 3-phase 4-wire, 4 wires, 3 hots and a neutral on our Y connected system. Now, discussion. So I'm going to get a little bit into the difference between Theorists and what the NEC says. And in the 2008, when they came up with the definition of neutral and they added neutral point, it started to take the theorists, which said, wait a minute, if I have a black and a white in a non-metallic sheath cable, the white wire, if we understand the neutral, it's to carry the imbalanced load. Okay. Well, in a black and white circuit, okay, ignoring the equipment ground right now, just the black and the white, whatever's going out, let's say you have 10 amps on the black, then you're going to get 10 amps on the white. It's alternating current, but again, it's going to have it. So is it carrying the maximum unbalanced load? No, it's carrying the load, no different than the hot conductor, right? The black. So the purists say, well, it cannot be a neutral, but it is a grounded conductor. Because as you'll see in an illustration here in a minute, it is connected to a grounded system. So it is a grounded conductor. But the theorists, the purists will say, yeah, but it's not really a neutral because of how it's the definition of neutral, at least to the point where the code panel had to get neutral conductor into the code, okay? All right, so let's kind of look at this discussion. It says, however, we're starting right here. However, it says the grounded conductor, which it is, in a two-wire circuit consists of one ungrounded conductor, that's the hot, and one grounded conductor from the system having a neutral point is now, let's check it out, is now defined as a neutral conductor because it has a neutral point in where it's connected. So the theorists still will go and say, yeah, but it's not carrying the maximum unbalanced load between phases. It can't be a neutral. Well, because of its conductor's connection to the system, and that's a grounded system, because of these definitions, it's now considered a neutral conductor, even though it's more properly termed a grounded conductor. That's why I tell you, you can have neutrals that are grounded conductors, but you have grounded conductors that are not necessarily always a neutral, okay? And we'll see that in a second. And an example of that will be a kind of a corner grounded delta, but we'll go to look at this here. So let's kind of look at this discussion because this is a neat discussion here. It says, although many electricians have long referred to a two-wire circuit with a grounded conductor as a neutral, most electrical theorists, okay, folks in the know, right, have stated that a neutral conductor must carry the unbalanced current from an ungrounded conductor to be considered a neutral, okay? So that's what we just talked about. So they'll argue that it's not a neutral because it's not doing that. Well, check this out. Based on the definition of neutral point, which is added in 2008, and neutral conductor, the grounded conductor of a two-wire circuit is indeed a neutral if it originates from an electrical system that has a neutral point. So the semantics of theory versus what the code says something is for the use of the NEC. Okay, so to use the NEC, when we're looking at it and saying, well, I need to know what to call that white conductor in a two-wire system, we know it's grounded, but now we know the code says, based on its neutral point on that system, that it is also taken as a neutral, okay, not just a grounded conductor. See how it kind of works? All right, so NEC clarified that. So it says, based on the definition of neutral point neutral conductor, the grounded conductor of a two-wire circuit is indeed a neutral because it originates in an electrical system at the neutral point. However, a grounded conductor from a very simple 120-volt single-phase two-wire system is not a neutral as defined, but still is required to be grounded and is considered to be a grounded conductor. Okay? So we'll acknowledge that it is not the way it's written, it is not a neutral in the purest form. Code's telling us to treat it as a neutral, but it is most certainly is a grounded conductor. So this is a difference between what the code is telling you something is and how to treat it when we're applying the NEC. But again, the purist at heart will say, yeah, but we all know that it's not really a neutral. We understand what the code's telling me to do, but in reality, it's a grounded conductor, okay? Now, we talked about this. The important distinction is made between neutral conductor and obviously equipment grounded conductors. We kind of know the importance of that. The equipment grounded conductor is only going to carry current under an abnormal condition, a fault condition, whereas the neutral conductor is expected, based on the definition, to carry current all the time at any given time. Now, you could have something that's balanced, right? You could have a neutral conductor and it's zero current traveling on it if you have 10 amps on A and 10 amps on B, and the neutral is going to see zero due to a cancellation effect, right? Well, that doesn't change the fact that it's a neutral, because if something changes and A is carrying 12 amps and B is now carrying 10 amps because some other load was turned on, then the neutral is going to carry what? The imbalanced load. It's going to carry 2 amps, okay? The imbalance between the two. So it is going to be carrying that current, and it could be carrying it at any given time, and it's expected to, right? So that's why it's a neutral conductor. All right, so it's important distinction. And again, while we talked about it earlier, improper case to neutrals downstream create objectionable currents, and it can put electricity, it can put potential current on metal components, especially if you make that connection, and for some reason you have a weak neutral connection and you lose that connection. Now you've got that return current traveling on metal parts, and that becomes a hazard. So there is many reasons why we have to distinctively understand the difference between equipment grounds and neutrals. Even though they connect together on the same bus in your service, once we go downstream, they must be separated, okay? All right. Now, we talked about the neutral point. So I think it's important that we at least look at the neutral point. So we're gonna go look at the neutral point real quick here. So this is a term that came in the 2008 edition based on that task group. Correlating committee set up this task group, and it looked at it, and they determined that when we're talking about neutrals, we're going to have to show how it's created, where the connection is for this neutral conductor. And we made reference to neutral point in that definition of neutral conductor, so it logically means we have to have a definition of neutral point. So here's what it says. It says a common point on a Y connection in a polyphase system, and that's that midpoint. We'll look at a graphic here in a second. Or the midpoint on a single phase 3-wire system. So again, that 120/240 volt on a winding, that midpoint connection, okay, that creates a neutral. Or the midpoint on a single phase portion of a 3-phase delta. So you have A, B, and C delta, and you're just taking a one winding, and it's the midpoint of one winding, okay, creating a midpoint, neutral point. And of course, it also talks about the midpoint of a 3-wire direct current DC system. Now, this little asterisk right here in our course just reminds you that this is verbatim out of the National Electrical Code. And then, of course, you have an informational note that's saying at the neutral point of a system, the vectorial sum of the nominal voltages from all other phases within the system that utilize the neutral with respect to the neutral point is zero potential, okay? So wherever you're making a connection, okay, in our system from the neutral point to all other phases, you're using the neutral point to get that reference, and it's considered the zero connection. Okay, that's also how we get stability in reading our voltages. Okay, again, this is an informational note. It's not enforceable, it's just information. Okay. All right, so let's look at this discussion. This was a new definition in the 2008 for neutral point. It says the term neutral has been used in the NEC for many editions and was never defined. Well, 2008 it was defined. The electrical industry previously relied on the definition of other standards like IEEE standards to try to define it. Most electricians didn't have that document, didn't have it handy. So it also kind of fell back on trade knowledge and hoping that your master who was teaching you or the school that you might have gone to was teaching you proper things. And because if we teach it wrong, then we propagate wrong things, right? So the hope was that they taught you right about the neutral conductor. The good news is all of that culminated in that task group looking at it in 2008, and I think they did a wonderful job of creating neutral conductor as well as neutral point to try to make things easier to understand. Now here's some illustrations. Now this figure right here that we're going to look at is electrical systems may have a neutral point with a grounded or neutral conductor under several configurations. All right, so let's kind of look at what we've got here. Let's look at each one here. So the first one, let's kind of move it up a little bit there. So this first one here is an example of a single winding. This would be a 120 240 volt single phase, single winding where it's tapped at the midpoint. So from phase to phase on this winding is 240, but from phase to center tap here on this winding is 120. This is the neutral point, and that is where the neutral conductor. So from here, and that's why the informational note was important for the reference. So from here to here, it's 120. From here to here, it's 120. From here to here, it would be 240. This is the neutral point between the windings, okay? All right, this is B. Now this is that example of this 4-wire, 3-phase Y configuration. Here's the center point, or the common point, right? So in this case, if this was a 120 240 volt, a 208 120, then this would be from here to here, it would be 208, right? But from here to here would be 120. This is the common zero reference point because this is connected to Earth. And so this is where you're going to get for voltage stabilization. And this is where the neutral is created, right here, okay? Number 3, so this is an example of a 3-phase delta 4-wire system that's derived from it. And right here, here's your midpoint. And right here is where you're going to get from here to here, it's going to be 240, or could be 480. And then from here to here, it's going to be in this winding, if this is a 120 240, then from here to here, this would be a 120. Right? So that is a neutral conductor in this configuration. Now, D is an example where we have a delta system here. And this is obviously an ungrounded delta. And then you have connections here that come down and hit a zigzag transformer. And in this one, there's a neutral point here. And then this system is intentionally grounded, creating this neutral conductor on this system. Now, notice this is derived from an ungrounded system. Right? So this is how you can create it as well. E over here, this is an example where we're talking about here. Now this example here is, see where you've got here, transformer, E here. Now I will also let you know that, let's see here, E right here. So this right here, so this one I wanted to show you in our program, we tried to give you explanations. So one of these things here, and we can talk, and you get all of this explanation. We're just kind of paraphrasing it. But if you look at E right here, and you see this is not a neutral point, okay? So this is not considered a neutral conductor. Now, it is connected to Earth, so it is a grounded conductor, but it is not a neutral conductor, okay? So this is an example where all of these are grounded conductors, but not all of them are a neutral conductor. And that's so important when you're looking through the code and you see a reference to neutral conductor. Very important. So if we go down real quick and look at that E one right here, it says, check this out. The system shown in figure 117E is of a 2-wire transformer installation. This system does not have a neutral point, and as a result, does not have a neutral conductor. The conductor that is being shown is being grounded in a grounded conductor, but not a neutral. In this case, either conductor could be grounded, but not both at the same time, obviously. Yeah. So it doesn't matter which one of these are grounded. This one just happens to be grounded. That creates the grounded conductor in this scenario here. But you don't want to treat this conductor as a neutral. It is grounded. It is grounded, but it is not a neutral for the terms in the National Electrical Code, and anywhere that it might make reference to neutral conductor requirements. Now, this one down here, this is F. F is a corner delta, and you see that this corner is connected to Earth, but it is not considered a neutral. And again, in our system, or our program, it makes it really clear right here. The system shown in F, which we're looking at, is a 3-wire, because it wasn't a 4-wire, it's a 3-wire, 3-phase corner grounded delta configuration. So even though it has a system conductor that is grounded, connected to Earth, the system does not have a neutral point as defined, and as a result has a grounded conductor that forms the 3rd phase for the 3-phase system. But it is not it is not considered a neutral conductor when it comes to the code. So there you go. Right? So there is no neutral point. So the whole point here was to be clear that grounded conductors may be a neutral, but all neutral conductors are indeed grounded conductors. And this illustration should point it out. And why is that important? Really, the whole point of this is when you're looking at the NEC and it's making reference to neutral conductors, you have to look at the system and determine in the system, is this a neutral conductor? If it's not, then those neutral rules aren't going to apply to it. So important to understand the differences in the baseline of what's considered a neutral conductor or not. Okay. Also in our program, I just want to point out, we have pop-up illustrations here. Again, this was showing, D was showing a delta configuration with a zigzag. That's what that was. So I just want to show you some of the features that are in our grounding and bonding. It really does get deep. Okay. So if you really want to learn grounding and bonding, this is the course for you, because again, at the end of the day, that's where most people make mistakes in systems, is they don't understand the grounding and bonding and they create hazards. Okay. You can go too far with grounding and bonding, or you could think something's a neutral when it's not, and it can cause a problem. So again, hopefully that cleared out. Now, what we're going to do now is we're going to, let me take it back to me real quick. What we're going to do now is go into part 2. In part 2, since we now have a firm understanding of the grounded conductor and neutral conductors, now what we're going to do is we're going to shift into services and the fact that we have to bring a grounded conductor to the service. And we have sizing requirements, minimum sizes. So we're going to talk about, you have to do a load calc, right? To determine what that unbalanced load is for sizing our neutral. But then there's also considerations under 250.24D that you have to take into consideration. And ultimately, that's going to send us to 250.102C and the tables. So we're going to cover that in the next episode. So this was part 1. Hopefully you got something out of that. A little more clarity when it comes to the neutral conductor, and understanding that there's a difference in the two and what derives one. And then we're going to go into part 2, and we're going to show you how that applies to the service applications. Hopefully you got something out of it. We'll see you in part 2. Hey folks, hopefully you're enjoying this series on grounding and bonding as we're talking about the grounded conductor. If you want to learn more about the National Electrical Code, you want to learn about grounding and bonding, residential, commercial, industrial, you even want to learn about HVAC electrical if you're an HVAC technician, if you're preparing for an electrical exam, we have the courses that can help you. Do me a favor, go over to our website, fasttracksystem.com, look around, watch some of the demos. You will see that our academy teaches you what you need to know about the National Electrical Code. I'm excited about the future of our academy. I'm excited to teach you. So hopefully you'll join our family and become the next member of our Fast Track community. Take care. Oh, and stay tuned for the next video. Hey everybody, Paul Abernathy here. Thanks for joining me in part 2 of our grounded / neutral conductor educational series here at Electrical Code Academy. Now, before we get started into part 2 here, we're going to be looking at grounded conductors that are brought to the service, and we're going to be talking about sizing so we can clear up all this requirements for what's the minimum size grounded conductor. And we're going to learn about all that, but before we do that, I want to make sure that you watched part 1 of this 2-part series. The reason is, part 1, we talk about what a neutral conductor is, what a neutral point is, what a grounded conductor is, and what creates a grounded conductor that is not always a neutral, but is always a grounded conductor based on where that conductor is connected in the transformer at the neutral point. We also talked about how this was created in the 2008 edition of the National Electrical Code So what we might enjoy today in the 2023 edition wasn't always the case. So clarity had to come from a task group back in 2008. So I want to make sure you go back and watch part 1 before you jump into part 2. Okay. All right. Assuming you've done that, we're going to kick into part 2. Now, what we're going to talk about here is bringing the grounded conductor to the service equipment. And we're going to talk about the sizing for that. And we might even dig into some little things here and there about it, but that's our focus. That's what we're really going to try to key in on today. And we might go down a rabbit hole and talk about a few things, but that's our focus. We're going to be keying in on that grounded conductor. Okay, so let's go on and go to the lesson. All right, so we're in the 2023 edition of the National Electrical Code. And I will remind you that, as you see below, the Fast Tracks Black exam preparation program is out for the 2023 edition. It's been revamped for this 2023 edition. So check that out if you're interested in it. It really will teach you the National Electrical Code at a much higher level. Now, what we'll be working on today is out of our grounding and bonding course for the 2023 edition. So I want to make that distinction because a lot of people will see this and think, well, this is what I need to prepare for an electrical exam. No, this is just grounding and bonding today. If you're preparing for an electrical exam, this is what you want. Fast Tracks Black or even the Fast Tracks Plus. The only difference is the Plus gives you access to a bunch of videos, probably like this video, over on fasttrackstube.com. So again, that's really the only difference between the Black and the Plus. All right, let's get into it. So we learned in lesson 1 or part 1 what a neutral conductor was and what a grounded conductor is. Now, we're required to bring the grounded conductor to the service. Now, whether we need the grounded conductor beyond the service is irrelevant. At this point, we know what we need to bring to the service. So let's kind of look at it. And I'm going to read where necessary to add additional context to this. So we're at 250.24D. Now, if you're in a previous edition of the NEC, it might be 250.24C. So again, we're working out of the 2023 edition. All right, this says the grounded conductor brought to the service equipment requirement. And again, this is paraphrasing, or in most cases, this is a direct quote from the National Electrical Code. So keep that in mind. It says, if the AC system operating at 1,000 volts or less is grounded at any point on the system, and this would be back up at the utility transformer, it says the grounded conductor is required to be routed with the ungrounded conductors to each service disconnecting means. Okay, so the reason we're routing it with the ungrounded hot conductors is because of impedance. We want to keep them all together so we don't have an elevated impedance, because you got to remember something. That grounded conductor from the service equipment back to the neutral point, and again, that's why it's important to watch part 1 in this video, that's also going to be carrying fault current to allow for the clearing of overcurrent protected devices. Critical thing to keep in mind. A lot of people just say, well, it's just the grounded conductor. It's only carrying the maximum unbalanced load. Yeah, but it's also carrying fault current when it tries to clear an overcurrent protected device. It's a very important fundamental thing in grounding and bonding and why they're so similar, but yet different. All right, so reminds us to do that. And where are you going to bring that grounded conductor to? You're going to take it to the grounded conductor terminal post or terminal bus, okay? A main bonding jumper is required to connect the grounded conductor to each service disconnecting means. Okay, so the main bonding jumper could be a green screw. But let's say it all wasn't done on one bus. Let's say you had an equipment grounding conductor bus and you had the grounded conductor bus. They're required to be connected together, but that conductor that connects the two together is a main bonding jumper as well. All right, so it could be all on one bus with a green screw, or it could be two separate buses, but if they got to be tied together, and that would be a main bonding jumper as well. And of course, we size main bonding jumpers in accordance with 250.28. Okay, so again, now it tells us the grounding conductor must be installed in accordance with 250.24C1 and 250.24C1 through C4. Now, for us today, this is what we're going to be focusing on, because we're talking sizing of the grounded conductor and all the things that have to be taken into consideration for that. So we're going to be breaking that down. Remind you, we have other videos, and this course is very extensive when it comes to grounding and bonding, all the nuances. So again, if you're looking for a good course for grounding and bonding, this is the course for you. All right. Discussions. Now, this is another beautiful thing in our program. This is like sitting in a room of people having a discussion about various topics. Discussions are added into here, whereas a lot of times when you get books, it's just code. Here is a discussion, very important. And it says, this code section provides another critically important requirement in Article 250. If an electrical system supplying the service is grounded elsewhere, typically it's done at the utility, it says the grounded system conductor, which usually is a neutral as well, must be run to each service disconnect and be bonded to each service disconnecting means. Okay, so that's why we bring the grounded conductor in, we take it to the bus, and the bus has a main bonding jumper that connects it to the cabinet. All gets done at the service, right? It says the discussion in 250.24c, this grounded conductor provides the critically important path for ground fault current back to the source to complete the circuit. So many times, again, this is missed. When we're doing a calculation for neutral loads, that's one thing. But we also have to remember, or grounded conductor loads, we also have to remember that those conductors all the way back have to what? They have to be able to handle ground fault current as well. So we're not talking about from the load side of a service disconnect where we have equipment grounding conductors. All right, that just brings it back to the panel. But it has to complete that loop all the way back to the source for that overcurrent device to function. And that main bonding jumper bridges that gap over to the grounded conductor from any enclosure that gets back to the source. Critically important to have a main bonding jumper, but critically important to make sure that those grounded conductors are sized properly as well. Okay. All right. So this complete circuit path current permits current to flow through the overcurrent device that is in series with the fault current and will allow the device to open and clear. Okay. All right. The requirement to route the grounded system conductors with the phase conductors, I talked about this earlier, is keeping all of those conductors in close proximity routed together is to do what? It's to limit the amount of impedance. And impedance is AC, whereas resistance would be a DC. It's all in opposition to current flow. And when we're trying to clear an overcurrent device, the last thing that we want is resistance to oppose that current flow. Remember, we want that current to skyrocket so that that overcurrent device will activate. It's inversely proportional. The higher the amount of current, the quicker that overcurrent device or fuse will blow, right? So that's what we're trying to achieve. So making that system complete is vitally important. All right, now it says, so we're doing this to reduce, keeping them close together to reduce the effects of impedance or elevated impedance. And we would have discussed this early in this course, that it's essential to maintain that low impedance in order to make sure that the overcurrent device is clear quickly, okay, to eliminate that hazard. All right, this is important because the grounded system conductor serves a critical role in that fault current path. Absolutely, it does, all the way back to the source, okay, of the system. So this is kind of an overview, and this kind of also allows me to illustrate where we talked about the possibility to have separate buses, okay, and how they have to still be connected together. Okay, so we do this because everybody's familiar with the one neutral bus that has the green screw in it, and it's all connected. You bring the grounded conductor there. We're all familiar with that. But how often do you see where in the service equipment you have separate buses? And so this is your equipment grounding conductor terminal bus, but it has to be connected over to the grounded conductor bus, and it can't be through the metal enclosure. So this right here, it's got to be directly connected. Okay, so here is the main bonding jumper in this case. Now we could eliminate this, take this bus out. We could take this ground screw, this main bonding jumper. In this case, it would be the main bonding jumper, and connect it over here onto this bus, and now the green screw is the main bonding jumper. Okay, so in this setup, this is the main bonding jumper that connects the enclosure to the actual grounded conductor. But if we got rid of this and we had it all on one bus and we put the green screw in, then that's your main bonding jumper. Oh, and by the way, I would not have to size that green screw. It's already done by the manufacturer. In this scenario, I am going to have to size this, because this looks like a wire type main bonding jumper. I'm going to have to size this based on 250.28. Okay, so just keep those things in mind. Not for this episode, but we have episodes on that if you want to learn about sizing main bonding jumpers. Key thing to remember is an equipment that comes with a green screw, that's it. It's already done. Or one of those little straps that comes with it, it's already done. You don't have to do any calculation. But if it was a wire, then you got to calculate. Okay? Or if it's a bus bar, you have to calculate. All right, so here we go. We're all done. Okay. Now this is showing an example in 250.64D1 where the grounding electrode conductor can be connected on the supply side to the grounded conductor all the way up to the service point, right up here. So anywhere in here, it could be a connection for this grounding electrode conductor. But the main thing about this is showing you that this is the still service conductors. This is a tap, which is not a feeder tap. This is a service conductor still, okay? So they're going to be going up and they're going to be coming in here. And the size of this grounded conductor is going to be based on these conductors here, right? And the size of this grounded conductor is going to be based on these conductors here, okay? And we'll cover all of that, right? So again, this is a grounded conductor here, and it's run to each separate service enclosure. This is an example of also where you could have it run, the grounding electrode conductor could be run to each service enclosure, right? Again, this grounded conductor here is sized based on what? These conductors here, right? And this one's sized on these conductors here. We're going to get into all that. Don't worry. All right, so let's kind of look at a discussion a little bit here. So we're going to be talking about this illustration right here. 2-26, so give a good look at it. Okay, you can pause if you need to get a kind of good look at what we're doing here. We are making a connection to the grounded conductor on the supply side. We're also able to bond this enclosure, this wireway on the supply side. That is 250.142 allows me to use the grounded neutral conductor to do that. All right, but anyway, let's talk about this discussion real quick. It says, as illustrated in 2-26, it said, this is important that the grounded service conductor be installed in each service enclosure and be connected to the enclosure, again, using a main bonding jumper. Even though the grounded conductor, often it's the neutral, may not be used beyond the service, means you bring it to the service, but maybe you don't need it downstream because maybe you have only three-phase motor loads that don't need a neutral. Whereas in the other panel, you need a neutral, okay? So you brought the neutral to the service equipment. Beyond that, you may not need the neutral at that point. So it uses this illustration. It says, this is often the case when a single-phase service disconnect and a three-phase service disconnect are installed from, or they're derived from, a three-phase four-wire Y or delta connected system. Often the single-phase service supplies the lighting and appliance loads, okay? And the three-phase applies things like the motors or other three-phase loads. The grounded conductor from the three-phase service provided the low impedance path back to the source, even if a line to neutral loads are not even supplied within that panel, okay, by the service, okay? So this is a good example. So here we've got the grounded conductor that's bought in. Now, even here, if we were to go out of this three-phase disconnect here and service disconnect and go out to three-phase loads, right, you're still going to have equipment grounds. You don't get rid of that. And it comes back and it's still going to facilitate the operation of the overcurrent device because it's going to allow it to get back through the grounded conductor back to the source, even if we didn't need the neutral or grounded conductor on the load side of the service disconnect. Over here, since we're coming off here, then chances are on this system, single phase, this is going to handle lighting and receptacle loads that are 120-volt loads, and it needs a neutral. So again, this is a classic example of how you would have a three-phase, four-wire system, and you're deriving off of it a panel that's doing just single-phase loads, and over here, three-phase loads. Okay? But you notice the grounded conductor is bought here, and it allows for that fault current to get back to the source, still have to clear overcurrent protective devices, right? Great illustration to throw that out. Now, the grounding electrode connection to the neutral, as we see right here, is permitted to be done in multiple locations in 250.64 D1, D2, and D3. All right. So in this case here, we're seeing it done here on the supply side. Okay, so that's perfectly one of the allowances to do that. So the grounding electrode conductor to the neutral is shown in the wireway in this illustration. It's done up here, right here. And that's what that figure is about. And that location is above the service system net. This is one of the few locations or connection methods that are permitted by 250.64 D1 through D3. Go look at those areas that you can do it, okay? Because you could come out of here and come to ground rods. Let's just use ground rods. Or you come out of here to ground rods if that's what you want. So you have multiple allowances to be able to do this, okay? So again, code's a beautiful thing. It gives you many ways to do it. We're only depicting one application here. Now, there is an exception that says, okay, well, what if I have two or more service disconnecting means in one single assembly, like switchgear or switchboards with vertical sections? Okay, so let's look at an example of that. Well, this is an example of that. So this is, again, would be example of switchboard, and these are separate vertical sections. Right? And so what you've got is a common bus that transverses through each one of these sections, and it connects over to the enclosure. And this is where all the main bonding jumper's done and everything's done here. But it gets done in this one common location rather than making connections in these separate vertical sections. This is permitted, right? And this is an allowance to do this, okay? This is one big listed assembly, right? All right, so now let's talk about sizing the grounded conductor. Now, let me talk to you a couple things about what you should know, and I'm going to get redundant here. And when I go into this, we expand this. The first thing that I teach students in our Fast Tracks program and wherever I'm at that I have an opportunity to teach, we always have to remember to do a load calculation. We have to calculate what is going to be the maximum unbalanced load. And that's given to us in 220.61. And that's part of part 3 of Article 220 for calculating. So if we're doing an optional calculation on a building, we have no way of doing the neutral calculation unless we use part 3, which is the standard method, right? So we're taking all of those neutral loads into consideration. And so it's critically important that we as students of the code know that that grounded conductor 1 has to be able to handle the maximum unbalanced load. Where does it say that? Well, we kind of got to go look at the code. And right here is where it tells me, right here in 220.61, which I'll remind you is, again, part 3 of Article 220, it says the feeder or service neutral load shall be, it's mandatory language, shall be the maximum unbalance of the load determined by this article, 220 being the article. The maximum unbalanced load shall be the maximum net, okay, calculated load between the neutral conductor and any one ungrounded conductor. Okay, so we're going to do a load calculation. We're going to determine it. And of course, we have some allowances for reducing the size of the grounded conductor. We have some allowances for that. Okay, and we have additional allowances when that value may exceed 200 amps. So we have some allowance to reduce the size of that grounded conductor. All right, now, one thing to remember, we have to make sure that we're handling our net value of our maximum unbalanced load based on a calculation that you and me have to do. Okay? So that's the first thing that we always should remember. Now, there are certain systems where you cannot reduce the size of the neutral. Just get that out of the way right here. So that is C. It says there shall be no reduction of the neutral or grounded conductor capacity applied to the amount in 220.61C, okay, 1, okay, right here, or portion of the amount in C2, which is right here, that from that determined by the base calculation. So if we have the neutral calculation and we do that calc as we just said we had to do, if you're dealing with these types of systems, okay, or you're dealing with the portion non-linear loads. A motor example would be a linear load. A non-linear load would be something like a variable frequency drive or fluorescent electronic ballast that can distort the waveform. If that's what you're dealing with and you're dealing with the full wire three-phase Y systems, then you can't reduce the neutral or grounded conductor. It's going to be full size to handle whatever the load calculation was. That's it. You reduce it, right? But there are systems where we can reduce the neutral. And they're all covered right here, all right? Talking about it right here where we have that system. So these things are important to make sure you do those load calculations, right? And it's so important that you understand that when it comes to this. Okay, anyway, I wanted to show you that the first thing that we're gonna do is we gotta do a calculation. Now, if you wanna know how to do the calcs, then I encourage you to watch our calculation series where we talk about single family dwellings and multifamily dwellings. And in our Fast Tracks program, that's Unit 8 and Unit 11 and even Unit 13, we go over neutral calcs, okay? So you understand how to calculate the neutral loads, right? All right, and we apply any reductions that we're allowed to apply. Okay, all of that's covered in that series. All right, so just remember, make sure you do a calc to find out what the size is that you need to handle your maximum unbalanced net grounded conductor load. That's the first thing, okay? Now, we can go back now and see what the minimum size of that grounded conductor has to be. All right, so in your code book, you're going to be looking at 250.24D1. So this is sizing. Now, the first thing is we're talking about here is this is a single raceway or a single cable, or it could also be a single metal wireway, okay, connecting two cabinets. If all of my conductors are running through it together in one raceway, then guess what? We're going to follow this rule here for sizing the grounded conductor as a minimum size. Now, in it later, we're going to be talking about what happens if I break this up into separate raceways. But right now, everything we're talking about right now is in one raceway or one wireway. And I'll show you some illustrations to hammer that home. Okay, so let's look at the sizing rules here. This is 250.24D1. It says, the grounded conductor is required to be not smaller than specified in table 250.102C1. So that's pretty straightforward, right? It can't be smaller. Now, could it be larger? Absolutely. That's why I told you about doing a load calculation. If the load ended up being greater than what's in the table, then you go with what's greater. Straightforward, right? But it can't be smaller than the values that are given in table 250.102C1. First major thing to remember. Next thing to remember that in sizing that grounded conductor, it's not required to be larger than the largest ungrounded conductor or conductors in that raceway. That's the next important part. So if I had one raceway and I had 600 kc mil ungrounded hot conductors, and I were to go back to 250.102C1, and it was going to tell me the size of that grounded conductor, the minimum size, but in no case does it have to be larger than what? The largest ungrounded service conductor. Never has to be larger than that. So it would never have to be larger than 600 kc mil. Make sense? So that's the importance of this statement. Again, we're talking one raceway. Now, discussion. The requirements for sizing the grounded conductor in this section are intended to ensure that the grounded conductor is large enough to carry fault current back to the utility transformer. I hate to harp on this, because again, the whole reason is that even though we're sizing from the service out, that's equipment grounded conductors, we're sizing it based on the overcurrent protected device for those equipment grounded conductors because of the fault, ground fault. Once it gets back to the main panel, that fault current still has to get back to the source in order to facilitate that operation of the overcurrent device through that main bonding jumper. So those grounded conductors have to be able to handle that fault current. So that's why we go to 250.102C1 and pick it from that table, right? That's why we're doing that. Okay, just wanted to make sure that you understand that logic behind it, okay? All right, so the reference in the title of 250.24D1 indicates that these size requirements that apply in all service conductors that are in a single raceway or cable. A good example of that might be a type MC cable, type TC cable, whereas that's one cable assembly. Okay, so that's what it's referring to. Now, conductors in a single raceway can either be single conductors, or you could have sets of conductors done in parallel in a single raceway. Like you might have an EMT, whereas you might have two sets. Maybe you're running two sets of 4-aughts or two sets of 350s or whatnot. And maybe your raceway is large enough and you're not exceeding the 40% raceway fill that's covered in Chapter 9, Table 1. So maybe we're okay. And that's all in one raceway. Okay, so that's what it's saying. We're simply talking about one raceway. Now, figure 2-26, and that's what I wanted to show you, 226. That's this one here, right? This shows you that this is in one raceway. Everything here, okay? And you see that it's tapping off here, and it's tapping off here, okay? Just making it clear. We're just reiterating that in the discussion. And I wanted you to see the illustration so that you go, what illustration was that? All right, is an example of the requirement where the single raceway supplies a single wireway and then is connected to each disconnecting means enclosure. So you saw it went from one raceway coming in, went to one wireway, and then it broke off to two separate service disconnecting means enclosures, okay? Another example is shown in 2-24 and 2-28. Well, we'll stay at 2-28 because 2-24 is kind of the same scenario. Now, figures 2-24 and 2-26 show a single raceway that supplies a wireway. All right, so again, 2-24, I guess we'll go back and look at it. Let's go on back and look at it since we're talking about it. So here you see a single set here tapping off and supplying two separate enclosures. And then 26 is the same thing, a single coming in, and it's tapping off and hitting two separate enclosures. Same concept, right? Now, figure 224, which we just looked at, and 226, again, show that. Now, figure 228, which is right here in front of us, shows an individual set of service interconductors from the current transformer, and now it's broken off into what? Individuals. One's feeding this cabinet, or this enclosure here, and then this one's feeding this one, okay? So this is just a CT, so this is still service conductors, by the way, coming off. And so this grounded conductor here is going to be sized based on these conductors here. And this grounded conductor here is going to be based on the size of these service conductors here, okay? Remembering that it's still going to be based on the size of our calculated load for our maximum unbalanced load in 220.61. Never forget that. Okay, so remember, what we're looking at right now is a minimum size requirement. It could be larger based on your calculation. Always remember that, okay? All right, so that's what we got here. Now, in this case, the grounded conductor routed with the phase conductors, these right here, coming from here, must be larger, must be the larger of the calculated load in basically 220.61, or again, from table 250.102C1, okay? So keeping all that in mind here when we're doing these calculations. We're going to get into examples, but that's what we want to show you, the distinction. Here, based on these conductors. Here, based on these conductors here. Okay? Straightforward? Okay. Don't worry. Don't worry. We're going to get into deep. We're going to get deep here. All right? So now, so basically, 3 steps are required to properly size the grounded system. Remember, we're still talking about just one raceway here and treating each raceway. Again, these aren't parallel. These are separate, okay? Separate sets that are being run to 2 separate enclosures, okay? So we're still dealing with the one raceways. All right, so 3 basic steps are provided. And there could be 1 4th step if you have an engineer design involved, but let's look at it. So first thing you want to do is perform a load count. Okay, we should say that every time, because you're going to do it. Make sure you learn how to do it. Next, gives us the minimum size required to carry the maximum unbalanced load from the ungrounded conductor. So that's the next one, okay? So we did that, and we need to size that neutral conductor. So we did that. That's why we did the math. Next, we're going to determine the size or the minimum size based on the largest ungrounded service conductor for reference in each raceway to table 250.102C1. Okay, so in this case, we're taking the conductors from here. Say this is 350. We're going to take that 350. Then we're going to 250.102C1. Okay. And we do the same thing for this raceway, for this grounded conductor. Okay. And then third, we install the largest ungrounded, the largest grounded or neutral conductor based on the difference in those two, whether it's 220.61 or 250.102C1, whichever resulted in a larger. Now, between me and you, typically, you're probably going to have the calculation yields the larger grounded conductor or neutral conductor, but you've got to be careful because it may not. And ultimately, you could do a calculation and then you end up running over to 250.102C1 and you go, oh crap, it can't be less than that. Okay, so important to be aware of that. Now, of course, the fourth thing that might come into play is if it's an engineering design. If an engineer designed it and they just made the grounded conductor the same size as all the ungrounded conductors or larger or whatever they did, right, then you're going to follow the engineering's drawings. Because ultimately, at the end of the day, they're the ones that are designing it. They're the ones that are putting their stamp on it. So that's what they want. You may agree to disagree based on the code calculation on the load, but that's their choice. And usually they probably did a load calculation. So they're the ones that are making this decision. Okay, so you're going to follow them. So really three factors, but there is a fourth element if it's an engineered design system and they, for some reason, make it larger. Okay. Now, for each of these that we just discussed and similar installations, use the largest size of the service ungrounded hot conductors in the wireway or raceway in the first or second column of table 250.102C1. And we're going to look at that table, okay, based on whether the service conductors are copper or aluminum, okay, and the third or fourth column in that table are used to determine the minimum size conductor permitted to be used for the grounded neutral service conductor, as well as the minimum size bonding jumpers that are covered by this section also. Don't forget, folks, that 250.102C1 is minimum size grounded conductor, but it also gives you direction on sizing supply side bonding jumpers and other bonding jumpers. So like main bonding jumpers will ultimately be referred back to this table. So keep all that in mind. Even though we're focusing on the grounded conductor today, that table is very useful for all of those other sizing as well. Okay? All right. So real quickly, and we're going to look at an example, but let's go look at that table so we kind of know what's going on. And I'll go on and get us kind of preloaded here. Bear with me. I didn't have it loaded, so I'm going to load it in. So when we go there, we know what we're doing here. So let's go there now. All right, so 250.102 is where we would be, but of course it sends us where the rules send us to the table. So we go look at the table, and here's the table, and you see right here it says grounded conductor. Okay, so here's where we're at. So notice that it says the size of the largest ungrounded conductor. So if I had one raceway and I had 350s in it, okay, those are my ungrounded hot conductors, and we did a load calc, and that's the size of the ungrounded conductors. What's the minimum size of the grounded conductor? And again, we have to do that load calc, but if we were just going to go to the table and say, well, it can't be smaller than this, what would it be? Well, if it was 350s ungrounded conductors in there, then we go down here. Since we're only going to worry about this part here, right there, then we would go down here, and it was 350, so it would be over 3/0 through 350. So when it says through 350, it includes 350, and that's also 350,000 circular mils or 350 kc mil, and you get that by this up here. So see that kc mil? That's reminding that this is 350 kc mil. Okay, K being kilo. All right, so you can take that 350 times 1,000, and that'll get you your circular mil. Or you just know that 350 kc mil is 350,000 circular mils. All right, so go over here. If we have a copper grounded conductor right there, then it would be what? It would be a 2 gauge. If it was aluminum, grounded conductor, then it would be a 1/0. Okay, makes sense? So you simply just go right here and guess what? That is the minimum size of your grounded conductor to go in that raceway. Right? Makes sense? Now, what about if we had that single raceway, like we had that picture of that wireway that had 2 sets in each? Okay, same thing. The only difference here is we're going to take, you have 2 sets, which has an ABC and a grounded conductor, and then an ABC and a grounded conductor. We're just going to take one set of A's, or take the one phase, the largest ungrounded conductor from each set, which is, let's just take A phase, because they're both the same, they're running parallel. So we take the A's. So let's say we ran 2 sets of 350s, and it went through one raceway. Then that's going to be 350 times 2, okay, because that's A phase, you have 350 for each. Add them together, that's the summation, and that becomes 700 kc mil. So what size is the grounded conductor in that single raceway when it comes to the summation of those parallel conductors? Well, let's go looking over here, and you see right here it says or, let me scroll up a little bit, or equivalent area for parallel conductors. Well, that's why we take the 350 and the 350 from the phase A, let's say, of the 2 sets, and we add them together. And that's where we get the 700, 350 and 350. Well, if that's the case, we're going to go down here, and well, let's see, over 350 through 600, well, that's not going to work. So we have to go over 600 through 1100, and that 700 falls niftily right in there. And so that means it would be a 2/0 copper or a 4/0. Let's see, is that right? Let me make sure I'm looking at it right. Hold on. There we go. Okay, yep, 700. No, excuse me. It would be a 1/0 copper or a 3/0 aluminum. Okay, and that would be the size of our grounded conductor in that one single raceway. Okay, perfectly fine. Now, be careful, because in a minute, what we're going to do is we're going to separate that up into 2 separate raceways. Okay, then it's going to be different. Right? But keep that in mind, right? Because then paralleling rules kick in, and what we have to do for that. Okay, so anyway, there we go. Follow that, pretty straightforward. Let's go back to our lesson, and we'll continue on with the lesson. All right. So where we're at, okay, so let's see where I want to go to here. Okay. All right, right here. So for each of these similar installations, the use of the largest size of the service ungrounded conductor in the wireway or raceway, in the first or second column we looked at, that was what told you the copper or aluminum columns. And then, of course, the sizing of the grounded conductor is in column 3 and column 4, based on whether or not it's copper or aluminum. Okay? Now, it is helpful to recall that the size of the ungrounded conductor at this point is the driving factor for sizing that neutral, of the minimum size. It's the driving point. That's why we took those ungrounded conductors and used them with that table to be able to size it. So it's important to remember that when you're doing that. Okay. Now, this rule also, this is just a reminder, folks. The rule for also applies to type MC cable, or be honest with you, trade cable as well, that are installed for service conductors. However, be careful, since MC cable may have a smaller neutral, because it could have it. Again, if you do reduce neutral, then the neutral may be smaller because it's basically designed by the manufacturer, and they did a reduced neutral. But you also could have an equipment grounding conductor in there that is reduced in size. Remember, when we're sizing equipment grounding conductors, that's sized on the overcurrent protected device. So this is just a reminder that if you're buying a cable, the neutral may be sized smaller than the ungrounded conductors. And guess what? The equipment grounding conductor, typically, because of feeder applications, the equipment grounding conductor, because you're not going to have an equipment ground on the service, it's going to be on a feeder, it could also be what? It could also be sized too small to handle a parallel application. So that means you're going to have a special MC cable made or a special tray cable made to do this, or you're going to have to utilize some allowances in 250, 122F2, and that is where you're running parallels in a cable tray, for example, or raceways, whereas you get to run one full-sized equipment ground and you get to use the other undersized equipment grounds in each cable together to be able to allow you to be able to use off-the-shelf type of MC or tray cable. Okay, this is just a reminder, okay, to when you're sizing it, don't just go buy a cable and assume that the grounded conductor or even the equipment grounded conductor is properly sized. Just be careful when you're buying off the shelf, okay? All right, now, as shown in figure 2-28, and again, I'll just reiterate it, there you go, to kind of get you an idea of what we're talking about. As in this figure, okay, it says parallel underground service conductors supply a CT or current transformer cabinet for utility metering. Okay, it says the grounded conductor for the underground service conductors, okay, we're talking about the grounded conductor, must be sized on the basis of the larger of the calculated load, means we got to do a load calc, 220.61, or from table 25102C1, using the size of the ungrounded hot conductors in the raceway. Okay, so be careful. We either have to do a load calc or we have it. So again, just to point back here, okay, this grounded conductor based on the conductors in this raceway, this conductor size based in this raceway, okay, be careful how you size this grounded conductor. Okay? Essentially the same as we're doing down here. All right, but I just want you to be aware that we're still following essentially the same rules. Nothing's changing. All right, now, let's look at here an example. So, for example, if we have 350 KC mil ungrounded aluminum, okay, let's talk aluminum, service lateral conductors. Okay, so this is service laterals coming in. We'll say that's the service lateral. Okay. I like examples, by the way. 350 ungrounded aluminum service lateral conductors are installed in each raceway. Okay. Table 25102C1 requires a 2 copper or 1/0 aluminum. Okay, so 350 again, right here, right? So we're running 350s in each one of these. So here's the 350. We would go over to the code. And over 3/0 through 50, and there's where we get the 2 copper, and there's where they would get the 1/0 aluminum. Okay, so that's what we would have in this raceway. Oops, over here. That's what we have in this raceway, and this is the same size, so it would also be in this raceway. Okay. Now, and that, again, that's in for each raceway, but we're going to also remind you of something that is critically important. So that's just base information on how we're running this scenario right here, because I got to remind you something, right, as we get further into this example. And I want to show you an example of why you would say, okay, so that looks like it would just be 2 copper and 1/0 aluminum. All right, watch now. This becomes the minimum size required to carry fault current back to the source, okay, for the service equipment. Compare the size of conductors required to carry that maximum unbalanced load. So remember, you had to do a load calculation, right? Don't forget that. Now, at this point, you'd think you're done, all right? So it says the requirements of 310.10G on installing parallel conductors must be compiled, with as well. The smallest conductor generally permitted to be installed in parallel is a 1/0. Okay. So these are being installed in parallel. Okay. So go back to, let's see this illustration right here. Okay. These are coming and it's being installed in parallel. These on this side are not. This is separate, where this side is being installed in parallel. So we had the minimum size that's required for these raceways, But we also have to remember that if it's applications being installed in parallel, that it cannot be smaller than 1 aught. Okay? Remember those paralleling rules. All right. So don't simply stop and think that, okay, that's a minimum size and we're done. Again, always remember we have paralleling rules that have to be met. Now, let's look at something else. Now, what if we have a 3-aught copper conductor supplying the 200 amp service disconnect from the current transformer? And that is this here. So let's say we're doing this one right here. So we've done this, and now we're coming up here. These are not in parallel, by the way, on that side of it. So here's what it says. If a 3-aught copper conductor is applying the 200 ampere service disconnect from the current transformer cabinet shown in figure 2-28, which we just looked at, table 250.102C1 requires a minimum of 4-gauge copper or a 2-gauge aluminum grounded conductor. A larger conductor may be required if you did a load calculation. So remember, that was the minimum required size based on 250.102C1, based on what? That 3-aught copper that's supplying that 200 amp service disconnect. If the load calculation resulted in it being bigger than a 4 copper, then it has to be based on the load calculation. Okay? So remember, 250.102C1 is a minimum. Could be greater. Same thing goes for that 400 amp. And at 400 amp, they're saying, well, that grounded conductor has to be at least a 1-aught copper or a 3-aught aluminum grounded conductor based on a 500 kc mil supplying that 400 amp. Now remember, a 500 kc mil under the 75 degrees rules in ampacity 31016 is good for 380 amps. So as long as the calculated load does not exceed 380 amps, then you're okay. Then it can terminate on a 400 amp overcurrent device. We're talking about the hot ungrounded conductors. Okay, so that's what would be a 500 kc mil would be fine if your calculated load is not exceeding 380 amps. If it is exceeding 380 amps, then that 500 kc mil is not going to work because it's limited to 380. So then you would have to go up to a 600 kc mil. Okay, but that's the conductor you're going to use, the ungrounded conductor, in order to size the minimum size grounded conductor. So that's why we got the 1-aught copper or 3-aught aluminum, because if you go to this table, you're going to see that the 500 falls right here, and that's going to be a 1-aught copper or a 3-aught aluminum. So you see how that worked? And that is how we did that scenario. Now, the next question you're asked is, well, what if I have a single raceway and I've got parallel sets, and what if my parallel sets exceed this table? All right, so this table goes up to 1100, and again, equivalent area for parallel conductors. So if I have a single raceway, we're still talking single raceways, okay, whether it's a wireway or it's a round circular raceway. What happens if I exceed 1100 kc mil? Okay, well, if that's the case, now you're going to have to use note 1. Now, note 1 right here tells me that if the circular area of the ungrounded supply conductors that are connected in parallel is larger than 1100 kc mil copper or 1750 aluminum, it says the grounded conductor or bonding jumper, because remember what this table is used for that as well, bonding jumper sizing, shall have an area not less than 12.5% of the area of the largest ungrounded supply conductors or equivalent area for parallel supply conductors. Okay? All right. So keep that in mind. Let's go back and see what we've got to deal with. So more requirements. It says, in addition, for sets of ungrounded service entrance conductors larger than 1100 kc mil copper or 1750 aluminum, the grounded conductor must not be smaller than 12.5% of the area. We talked about that. So we'll kind of do an example here or kind of illustrate that, and maybe I'll give you like a mental picture. Now, this requirement covers installations in which the ungrounded service conductors are larger than specified in this table. Okay, that's when this kicks in. Note that table 250.102C1 covers ungrounded service conductors up to 1100 kc mil copper and 1750 aluminum. This often occurs when service conductors are installed in parallel because you're trying to get more amps, so you want to have smaller conductors to run, so you're going to break them out into parallel sets. And that way you get to use the ampacity from each conductor acting together. So if you had two parallels of, let's say, 500s that were 380 apiece, then you add them together in parallel, then you get 380 times 2. Okay? And so that's what you're trying to do. That's why we parallel, right? Okay. Or maybe the 500s are even too large. So now maybe you want to do is you want to have 3 sets and you end up with the smaller conductors in order to achieve the ampacity you want. But you install them in parallel because you want to install smaller conductors, but you want to take the advantage of getting more ampacity out of it by running parallel applications, okay? Just remember you have to follow all the rules in 310.10g for paralleling. Same characteristics, same length, same conductor material per phase, all those type of things. You have to make sure that you follow those characteristics because we want the current to divide evenly amongst those sets. Okay, so anyway, that's for a different time. All right, now let's see here. Okay, so for installations with service conductors larger than 1100 copper or 7050 aluminum, it says the minimum size of the ground conductor must be calculated using that basic simple formula. Okay, 12.5%. The typical installation of service with service entry conductors installed in parallel is shown in figure 2-29. So we're going to look at that figure. Keep in mind this formula determines the minimum size conductor for carrying also, don't forget that it's still carrying that fault current. So if it starts to not make sense, remember at this point, the table is addressing the fault current, not so much the neutral load calculation. So that's why it has to be a minimum size, okay? All right. So what are you doing here? You're adding together the circular mill area of one set of the parallel ungrounded conductors. Now one set means all of the A's, the B's, the C's, whatever you might have. If the service conductors are different size, okay, choose the set of conductors with the greatest circular mill, the larger, okay? Now, multiply the value by 12.5%, and this gives you the minimum size and circular mill for the application. So let's look at this. So this is what we're talking about. We're still talking one raceway, by the way, folks. See this right here? Still one. I don't know why that keeps popping up. Let me get rid of it. All right, see, this is still one right here. So we have parallel sets here coming through. We only take one set. We're only taking the A's, the larger conductor from each set. We have 2 sets. So we're taking the A's, all right? So here we go right here. So size the grounded conductor for the largest of the calculated load, which is 220.61. We already, remember I'm hammering that home. You got to do a load calc. Or it's got to be based on the largest set of ungrounded conductors from table 251.02C1. And if it exceeds that value in the table, then you got to use what? 12.5%. And that's going to determine the size of this grounded conductor. Notice there's only one in here. So even though we have parallel applications, if it's in one raceway, then we only need one. But we have to size it properly based on the minimums of 251.02C1 or based on our calculated maximum unbalanced neutral load. I'm going to keep hammering that home because I think you need to understand that both of those have to take place. Okay? All right. Now, if the calculation does not result in a standard conductor size or the size smaller than 250 kc mil, for example, refer to table 8 of chapter 9 and you're going to round up. So what this means is if you're doing a calculation here and you do the 12.5% and it doesn't exactly match a conductor, then you're going to go back into chapter 9, table 8, which is where you go to get the circular mills, and you go to the next size. You get to round up, okay, to the next size per that table, okay? And I'll show you an example of that here. Well, let's do that now because I want to make sure I hammer that home. So if you go back, let's say that we did a 12.5% and we got 162,000 circular mills. And we needed to have the grounded conductor had to be equal to 162,000 circular mills. Okay, well, chances are there's not a conductor that is perfectly tailored to that, right? So we're going to go back here and we're going to chapter 9 we'll go to table 8, and that's conductor properties right here. And what we're looking for is the circular mill, which is the area. So notice it says circular mill and then it's titled area. That's what we're trying to do. And we go back and we had to have 167, let's say. So here we go. Okay, well, no, let's say we had 163, just to kind of show you the concept here. Well, 163 falls between a 2/0, which is 133, 100, and a 3/0, which is 167. So if it was 163, was whatever we came out at the 12.5%, then since it doesn't have anything in there, we got to jump up to the next standard size, which is a 3/0. So we would use a 3/0, which is good for 167, which is more than capable of handling the 163 or so that we came up with the calculation. You get it? So that's what it means by being able to go to the next larger size. That's what you're going to do. All right, now for some standard values that you don't have to do the brain surgery, if you want to just kind of commit things into memory, because they are very consistent, is look at it this way. So then this example that we're looking at on the screen is still one raceway. Okay, this is still this kind of scenario right here. Or this could be one EMT, or this could be one rigid conduit. Right here, it's showing you right here, like a wireway or extra wiring space, like a gutter or something. This is all one space, okay? So this is all considered one raceway. So that's what that's what we're still looking at here. So here's some non-rule of thumbs. These are actually calculations that we're just saving you the legwork, right? So if I had a 1,000 amp service and it was being supplied by 3 sets of 400 kc mil, okay? So in this case, 400 times 3, you just take phase A from each one of these sets. 400 times 3 is 1,200. Now 1,200 does exceed what? 1,100 kc mil of copper. And we're assuming copper unless stated otherwise. So what we're going to do is we'd have to take that 1,200, which incidentally is 1,200,000 circular mil. Or you could take that 1,200 times 1,000. And that's how you'll get your 1,200,000 circular mil. And we multiply that by 0.125, which is the decimal equation. Or you can take the 12.5 and move the decimal 2 places to the left to make it a decimal, and it's just much easier for your calculation. And that's going to end up being 150,000 circular mil. Okay, so 150,000 circular mil, we just kind of did that. If you go into the properties, which we will, we have to find a conductor that's good for 150,000 circular mils. Well, again, 133,100 for 2/0 is not going to work. So we have to go to the next size, and that'd be a 3/0, which is good for 167,800 circular mils, more than adequate for the 150. So that's what we do. We go to the next size. Okay, so that's how that works. And if I decided, because I want to go with smaller conductors for that same, maybe now I want to get a 1,200 amp service, or maybe I want to run 4 sets of 350 kc mil. Well, 350 times 4 is 1,400,000 circular mils, or 1,400 kc mil. And you just simply take that and multiply that by 12.5%, and that's where you get the 175,000. Same thing. If you go over to the table and look at the 175,000, you're going to see that it doesn't equate, because the 3/0 was 167,800, right? But the next size was 4/0, and 4/0 is 211,600. Well, that's okay. That can handle the 175,000. So guess what? I just go up to the 4/0. And that's all it's done here for you. Now, once it gets down to, let's say, a 1,600 amp service, and you've got 5 sets of 400, then in this case, 400 times 5 is 2,000 kc mil, or 2 million circular mil. Then when you do it at 12.5%, it equals 250,000 circular mil. Well, now you don't have to go to chapter 9, table 8 anymore. You know that that's 250. That equates to a 250 kc mil, and that is the minimum size grounded conductor. And of course, the same thing, you do the exact same thing for the 2,000 and 6 sets. Same concept. And this one, you don't need to go anywhere, because that equals 300,000, and you know that's 300,000 circular mil. That type of scenario. All right, pretty straightforward, right? So when you're doing a single raceway, pretty easy, pretty straightforward, not too awful complicated. Okay? All right, now this requirement and discussion that we've been talking about here assumes that all of the ungrounded conductors, the hot conductors, are to be installed in one raceway. Again, that's the whole premise, all in one raceway. All this we just did was for one raceway, okay? Such as in a wireway or a metal gutter that we just showed an example. All right, now, one ungrounded or neutral conductor can then be installed, like we saw the one, serve the return fault current conductor for all of the ungrounded service conductors. Again, that's what it's doing here, just one, okay? And that's how you would do it. Pretty straightforward, okay? Now, these larger installations utilize multiple conductors connect in parallel, electrically joined at both ends. Why do we do that? Again, we do it because we need to get more ampacity. And so we add more conductors, run them in parallel. They act as one. They act together as one. When you do everything correct under the paralleling rules, that's why it's important to follow those rules for paralleling. Once you do that, they act as one, okay? All right. So keeping that in mind, okay? So now this is a warning here. So the author is going to give you a warning here, and we're going to read this warning. It says, be careful about installing only one grounded conductor for sets of parallel conductors, since there may be compliance issues with 366.20 for auxiliary gutters, 376.20 for metal wireways, and 378.20 for non-metallic wireways. All three sections are dealing relatively with the same issue. The basic statement is as follows. So here's what it says. Be careful. It says, conductors connected in parallel, where a single conductor cables comprising of each phase, neutral, or grounded conductor of an alternating current circuit are connected in parallel as permitted in 310.10g. It says the conductors must be installed in groups consisting of not more than one conductor per phase, neutral or grounded conductor, to prevent current imbalance in the parallel conductors, such due to induced inductive reactance. Okay, now what does that mean? Well, look at it right here. It says, the issue here is to make sure that all of the magnetic lines of flux will cancel equally among all of the sets of parallel conductors. Okay, so we're not installed in groups. We're not installed in groups of A, B, and C and the neutral. Some of the conductors will have more impedance than the other conductors, and it's going to raise the heat level in one of those conductors. Okay, there could be a fairly large difference in current between one parallel conductor and the other one of the same phase. Okay, in one example of an actual installation, check this out. It says there were 10 500 kcmil conductors per phase. That's a lot now, 10 500s, and were not grouped as is now required for them to be grouped. Some of the 500 kcmil conductors were carrying as much as 500 amps. And remember, a 500 kcmil is only rated for 380 amps. But because of how it was installed, it was now carrying 500 amps, okay, with other of the 500 amps, with others in the same phase carrying a lot less. So it wasn't balanced out equally. And so it put undue current on one of the phases because they weren't run together. So again, all we want to do is make sure that you are aware that if you're going to do this in metal wireways, auxiliary gutters, or even non-metallic wireways, that you are very keen on the rules in the .20 section of those requirements. Okay? Now, it is common for design electrical engineers to specify that all service edge conductors, including ungrounded and grounded conductors, be the same size. Now, why did they do that? Because they don't have to go through a calculation. They just make them all the same size, and they don't have to do any calculation. Okay. Again, note the rules in paralleling, and take note of specific unique requirements, which we're not going to get into, but make sure you get into these unique requirements that are in 366, 376, and 378. Okay. Again, so it's your homework. Go check those out. Again, we're just sizing right now, so we're not going into these details. We're just talking about minimum sizing requirements. We're not getting into the paralleling and the effects of improper paralleling. All right. So that's it for the single raceway. Now we're going to talk about these grounded conductors that are installed in parallel raceways, 2 or more, and how you would size those. All right, so now we're in 250.24 D2. But guess what? Guess what? I said this was going to be a two-part series, but I decided to make it a three-part series because I think it's important to understand what you do when it's parallel sets and when they're done in separate raceways, what you have to do with that. So stay tuned for part 3. I don't like these episodes to go much over an hour, so I'm going to break it down, and I decided to go to a part 3 just on the fly because that's how I roll. So stay tuned for part 3, and we will get into what happens now when the grounded conductor is split into parallel raceways. Check you in the next video. Hey folks, hopefully you're enjoying this series on grounding and bonding as we're talking about the grounded conductor. If you want to learn more about the National Electrical Code, you want to learn about grounding and bonding, residential, commercial, industrial, you even want to learn about HVAC electrical if you're an HVAC technician, if you're preparing for an electrical exam, we have the courses that can help you. Do me a favor, go over to our website, fasttracksystem.com, look around, watch some of the demos. You will see that our academy teaches you what you need to know about the National Electrical Code. I'm excited about the future of our academy. I'm excited to teach you. So hopefully you'll join our family and become the next member of our Fast Track community. Take care. Oh, and stay tuned for the next video. Hey folks, Paul Abernathy here. Welcome back to part 3 of this series talking about the grounded conductor and sizing. In part 1, we talked about the neutral conductor, we talked about neutral point, kind of gave you a little history of it, kind of showed you some examples of how a system is derived to create that neutral conductor and all that. So if you haven't watched part 1 of this 3-part series, please go back and watch part 1 before you move forward. Then there's also part 2, and in the part 2, we focused on sizing the grounded conductor to the service, and we focused on a single raceway and how you might size the grounded conductor in a single raceway, and we included things like wireways into that, and so you could have multiple sets all in a single raceway, and you would have a single grounded conductor and how you would size that, remembering that that grounded conductor also is providing fault current back to the source. So all of this is important knowledge that you should take with you as you learn what a grounded conductor is and how it associates as a neutral. But now we're moving into part 3. Now part 3 is sizing the grounded conductor, but now we're dealing with parallel. That's 2 or more raceways or cable applications. So sit back and watch what we do here and follow along in your code book if you have it. We're again using the grounding and bonding program that's in our Fast Tracks program. And this is the 2023 edition of the National Electrical Code. So again, if you're looking in your code book and you're saying something doesn't jive, don't send me no email. We're working out of the 2023 edition. Okay, let's go to the lesson. All right, so what we've done is we've worked our way up to 250.24 D2. Previously, we did D1. And that's single raceways when sizing the grounded conductor, minimum sizing. And now we've moved up to D2, which is parallel, 2 or more raceways or cables. Now, I would be remiss if I didn't remind you that this is going to give us guidance on the minimum size of a grounded conductor. You still have to do your load calculation. You still have to understand 220.61. You have to calculate what the maximum net value for the unbalanced load is. That's the value after you've applied any reductions. And you size your grounded conductors, and in many cases a neutral, based on that calculation. What we're saying here is that it can't be smaller than the instructions that are given here in 250.24 D2 when you're running a parallel set. And ultimately it's going to send you to 250.102 C1, the table. Okay, that's a lot to take in, but that's what we're focusing on. Okay, and so this is a case where I'm going to be running multiple sets through multiple raceways, and I'm going to have a grounded conductor in each one of those raceways. How do I size that grounded conductor for that application? All right, so let's dig into it. So here's what we're looking at, 250.24D2. Got your code book. Look at that. And again, parallels, 2 or more. So if the ungrounded service entrance conductors are connected in parallel in 2 or more raceways or cables, the grounded conductor must also be installed in each raceway or cable and must be connected in parallel. So again, so that rule is basically looking at this illustration. If we're going to be installing these as 2 sets here, and they're being installed in parallel, instead of running them all in one raceway, they're running them in 2 separate raceways, so that's why we're at D2. This grounded conductor has to be sized for each separate raceway. And it's going to be based on the largest ungrounded conductor in each individual raceway. Okay? So that's kind of ultimately what we're going to do. Now, it also reminds us that it has to be in parallel. That is 310.10 is going to give us those rules depending on which edition your code you're in, whether it's G for the 2023 or H in previous cycles. Those are your paralleling rules. And so we have to follow all those rules. In this case, it's all paralleled nicely. It goes on to say that the size of each grounded conductor in each one of those raceways or cables cannot be smaller than 1 aught and must be sized in accordance with 250.24D2A or D2B, okay? And all of this is in accordance with 250.24D1, and all D1 is doing is sending you to 250.102C1, ultimately to do the final selection of the minimum size grounded conductor, okay? So we'll kind of walk you through all these scenarios here. So this is what we're talking about right here, parallel sets, okay? And we're going to size this grounded conductor based on this here. And we'll give you a bunch of scenarios. All right, now let's talk about this discussion. What is the process? The pretty simple process here. It's pretty much the same thing you did when we looked at part 2, treating each raceway separately, whether you have single set in there or multiple sets. If you have A, B, and C in a neutral, A, B, C in a neutral in one raceway, then you have 2 sets. You just take phase A for both sets and add them together, and then you go to 250.102C1, right? Simple. You do the same thing here. So it's not going to reinvent the wheel here. Each raceway is treated differently, okay? So I just want to reiterate that. The only difference here is you got separate raceways, so you have to have a neutral or grounded conductor in each raceway. Rather than just having one in a single raceway, here you'd have to meet the paralleling rules, and it got to be in each raceway. Make sense? So let's look at this discussion. This is the second method of installing conductors in parallel. The first method was D1, which was where everything was in one raceway. We already covered that. Here, identical sets of conductors are installed in parallel in 2 or more raceways or cables. So it's the same example that we did in D1 in the previous video, but now it's just breaking them up and putting them in 2 separate raceways. No different, okay? Now with this method, the set of ungrounded conductors connected in parallel is not normally larger than 1100 kc mil copper or 1750 aluminum. So think about this for a second. The reason that we parallel is ungrounded conductors, the hot conductors, because we need to get more current, more amps available. And rather than go with really big conductors, then we'll start going with paralleled sets and we'll get smaller conductors where you add them together, add all the A phases together, for example, and it acts like one larger conductor. Provided you follow all the paralleling rules, the current will divide evenly amongst all of those conductors that are run in parallel. Okay, makes sense. That's what that's why we do it. Well, when it comes to parallel sets in a grounded conductor, you also have to run that in parallel. Okay, and it has to be in each raceway. Okay, but since we have multiple raceways, the chances are you're not going to have ungrounded conductors exceeding 1100 kc mil copper or 1750 aluminum in any one of those raceways. That's the whole purpose of why we paralleled out, okay? So you're probably never going to run into that, and usually you're just going to go to 250, table 250.102C1, okay? All right, so what do? What's the sequence? What's the real world sequence here? Well, first we have to know what our maximum size of our ungrounded conductors are in this cable or raceway. How do we do that? We do a load calculation. and we size those hot ungrounded conductors. And if we need to parallel them in order to get the amount of ampacity that we need, we do that, okay? But that's what we need to do, and we're going to parallel them in separate raceways. That's the whole thing here. All right, so once we know what the size is of the ungrounded conductor in each raceway, next we're going to go look at 250.102C1 because we need to find what a minimum is. Now, don't forget, we had to do a load calc on this neutral conductor. We have to find out what neutral conductor has to be sized to handle the load, and we're allowed to parallel that, okay, divide it up amongst the raceways. But I still need to know what the minimum size is for each raceway. And the minimum size is going to be based on 250.102C1. So what do we got to do is we're going to go, and how do we get there first? Well, we get there by 250.24D2A and D2B. So here's what it says. Here's what A says. Okay. States that the size of each grounded conductor, okay, must be based on the largest ungrounded conductor in each raceway. All right, so let's go back here. So in this one, it's pretty straightforward. It's cut and dry, right? So you just take whatever, we'll just take the black. Whatever that size is for this raceway, we take that, then we go to where? We go to 250.102C1 and we size it. So if this was let's just say this was a 350 kc mil, then we're going to go to 250.102, go to the table right here, and we're at over 3/0 through 350, then it would be a 2-gauge copper. Okay, so we'll come back. So the minimum size grounded conductor right here would be a 2-gauge. Now remember, we're running these in parallel, so you automatically know that it can't be a 2. It would have to be at least at 1/0. But we're just kind of going through the motions, but that's how you would go to the table, okay? That's why I tell you, don't forget the paralleling rules, because they can come back and bite you in the butt. Even on an exam, if you're taking an electrical exam, it most certainly could bite you in the butt. All right, so that's what we know. So we've done that so far. So we know at least it's got to be at least a 1/0. And we're going to compare that to our load calculation, okay, and see which one results in the larger conductor. Now, 250.24D2B is a little different, and that is where you might have multiple sets in parallel in one of these raceways. And then you would do it the same way we did it in D1. If you got two sets in this one raceway, and it's ABC and a neutral, and an ABC and a neutral, okay, then you're just going to take the two A's and add them together. And so if there were two sets of 350 in there, then you add the 350s together, the two A's together, or the two blacks together, and that's going to be what? 700 kc mil. Then you go back to 250.102C1, the table, and you go down, and what size will we have to put in there for the grounded conductor, minimum size? Because remember, right here, it says equivalent area of parallel conductors. So that's what we're doing. So since it was 700, we're not going to be here. We're going to be over 6 through 1100. And that means now it's a 2/0 in each one of those raceways. And 2/0 is greater than the 1/0. So you would go with the 2/0, okay? Remember, we're still got to compare that to what? A load calculation, which might result in the grounded conductor even being larger than a 2/0, okay? All right, so keep that in mind, and that's exactly how it applies. Okay, so let's come back to the lesson. So that's your two options here. And that's how it's written in the 2023 edition of the National Electrical Code. Now, in the 2020, it's what it means, but it's not as cleanly spelled out here, but it's the same practice, same rules, but it's not as clean. That's why I tell people ask me all the time, well, why do we get so involved in code changes? Because we make things better. And this is broken out to make it clearer, okay? And that's the whole goal, okay? Now, remember again, the grounded conductor, often a neutral, cannot be smaller than 1/0, and we all just did that, and you get it, okay? So ultimately, that's how we had to verify. Now, I want to remind you real quick before we look at a delta connected service where you have a corner grounded delta, which is a grounded conductor, not a neutral. This is your logic chain that you have to go through. when sizing these grounded conductors. Number one, do a load calc. If my calculation, for example, was if I had 600 amps of neutral current, I'm just throwing a number, and I had 600 amps of neutral current, let's say after I've done everything, I'm just throwing numbers here, don't get technically beyond what we're talking about. And I take that 600 and I divide that by 3, then I have a 200 amp. So I have to have a 200 amp conductor in each one of the raceways, okay? You with me? So if that's what I'm sizing the neutral, if that's what my neutral load was, well, maybe that's going to be whatever that conductor size for 200 amps, right, would be what you need in each one of those raceways. Now, you have to go back and look and see, one, since they're parallel, it has to be at least 1 aught, so it's probably going to be larger than that for 200 amps in each raceway, okay? So now we're going to go back and look, and that's probably what, 3 aught copper? So we're going to go back and look. I think it's 3 aught copper. Let's go look, see real quick. If we needed a 200 amp in each raceway. Most of y'all probably already know that. But again, my brain is fried today. So let's go look and see what it is. And here we're at here. And we're going to be under the 75. We'll just stick with copper. And yeah, I was right. There. 3 aught. There's your 3 aught, 200. And that's what you have paralleled in each one of the raceways. So those are your, if we're dealing with the neutral conductor here. We didn't deal with the hots. We're talking about a neutral calculation here. So we did that. And so that was going to put a 3 aught. So that's larger than 1 aught. So far, the load calculation looks fine in each one of the raceways. Okay? Now, the second part of this is to compare that and try to make sure that we're going to beat the minimum size for that fault current 250-24D, and whether it's all in one raceway or in paralleled in multiple raceways. In our case, ours was, so we're going to go to D2. Now, D2 is going to kick us up to where? 250-102C1, and I'm just throwing numbers out there because I hadn't done the calculation. But let's assume that at this point, it's in separate raceways, and we have, let's say, let's just say, I'm just throwing numbers, 600 kc mil in each one of those raceways. Okay, so then we're going to go to 250-102C1 and just see what that would be. Okay, 250, bear with me. My eyes are still the way they are. So there we go. Okay, so now we're saying, okay, we're going to be 600. So this is saying it's got to be a minimum of 1 aught. So I'm just giving you ideas. So if that's the case, which is larger? The one that's based on the calculation, which was 3 aught, is larger. So that's what you would have inside of each one of those raceways. Okay, you see how that works? So in that case, the calculation resulted in the larger of the grounded conductor. Okay, so make sure you're comparing those two. Remember, this is a minimum when you go to 250-102C1. That's a minimum size. And then lastly, a consideration is the engineer. So the engineer may just throw out a size. And if that's the case, then it's got to be what? It's got to be sized what the engineer designed. And whether you agree with it or not, the engineer is taking responsibility for it, and that's what you're going to have, okay? Now, lastly, when it comes to sizing the grounded conductor, we want to talk about the grounded conductor that's from a corner grounded delta. So 250-24D3, delta connected services. It says the grounded conductor of a 3-phase, 3-wire delta service must have an ampacity of not less than that of the ungrounded conductors. So if you look at this illustration, this is a grounded conductor, but if you remember from our part 1, it is not a neutral conductor, okay? It is not a neutral conductor. And so, but it is a grounded conductor. So it comes from the system down, and as you'll see right here, it is connected to Earth, right? And it is not to be considered a neutral, but it is a grounded conductor. This grounded conductor size has to be the same size as these ungrounded conductors based on your calculated load for your overall service, okay? Whatever you did to size these ungrounded conductors, okay? The HOTS, that's what you would do, and that's what size this would be. Make sense? Okay. And that's about as far as we're going to get when it comes to sizing the grounded conductors. Bring it back to me. So here, part 3 was a short one, but hopefully you watched part 1, got a little better understanding, high level view of what determines the neutral point and neutral conductor. You saw part 2, sizing that grounded conductor for practical application based on a load calculation for the maximum unbalanced neutral net current and sizing for that, and then comparing it to 250.102C1. And we got there because of 250.24D1 or D2, okay? And so for a single raceway, D1. Now, if you had multiple raceways, like in this episode, then you're gonna use D2. And that's what gets you to 250.102C1, right? So remember, do the load calc, size to handle the load, in this case, the maximum unbalanced load based on 220.61. Make sure you do that. Then compare it to the minimum size grounded conductor based on 250.24D1 or D2, depending on your situation, okay? And lastly, check the engineer's drawings because they might just make it larger anyway, all right? All right, folks, I hope you got something out of this 3-part series. Till next time, stay safe. God bless. If you want more information on our programs, go right here to fasttracksystem.com. We'd love to have you in the Fast Tracks family. We do exam prep. We have grounding and bonding courses. We have commercial, residential. We have industrial. We even have HVAC electrician courses. Again, we have basics courses. All of that's available over on our website. We appreciate your patronage and sharing it with other people. And hopefully you learned something out of this video. Till next time, folks, stay safe. God bless.